So here's a notebook put together in Tephra2, and you have access to this notebook, and you can run these simulations anytime you want to. But let me take a minute and talk about the logistics of doing that, just so you get a good handle on it. If you go into the shared directory, you can go to workflows, and the workflows here developed. But what I think I want to show you most is the scripts, maybe? Oh no, wait, I'm sorry. What do I want to show you? I want to show you this README first. Okay, so this README explains how to run some of the workflows that are put on Victor, either for lava flows or Tephra codes. I know some of you have already done this, but we want you to get a handle on this. So what you do is you go to the shared folder and you copy this shell script. Okay, then you go back to your directory and you run that shell script. So I think it's under scripts. So I could copy this shell script into my Tephra2 folder in my directory and run that shell script. And so how do I do that? I just I'm going to show you an abbreviated version because I already did this. So I go over here, and here's my shell script. And if I go to where am I? If I go to a window, like a terminal window, okay, I'm here, and I can say bash, and then the shell script. I'm not going to do it because I already did it. But if you do that, a new directory is going to appear with the workflow for Tephra2, right? So all I'm doing is following the instructions right here, right? For that. For Tephra2, it's a nice model to start with because you don't have to worry about DEMs or anything like that. You can just start with that model. So again, just so you get the idea, I went into the scripts directory, I found this script, I put it where I want to run it. So here I am in my workspace, and I just typed bash, which is the command to run the script, and then I put in the name of the script. So I can just say bash. Since it's the only thing in my directory, I can say bash t tab, and it fills it out for me. Okay, and then I hit enter, and it runs the script. Okay. I don't know if Sam's still there. Do you have any? I think Sam might have left, but do you have, Sam, if you're there, do you have anything to say about that? I think you're gone. Okay, so that would create this directory, and I've got extra stuff in it now, but that directory, when you first create it, also basically is going to include this notebook. That's the orange square here, Tephra2 notebook. And so this is a Tephra2 workflow that Sam put together to sort of demonstrate how to use this code, right? And I just want to spend a few minutes going through it. I don't want to kill you with it in case you never want to run Tephra2 again. But if you have questions, this is a good thing to talk about in the Slack channel or something like that. Okay, so what we do is first we need some libraries to run this Tephra2 model. And I'm going to implement, so one thing I wanted to mention to you also, I forgot about it, sorry. I'm going to go back to this terminal for a second. And I'm going to change directories and cd to Tephra2, where I've got all those files. Well, one of those files is Tephra2 2020. And so that's the version of Tephra2 from GitHub put there in 2020. God, it's getting to be a long time ago. I can run that on the command line. Right? So when I do that // it means run that version of Tephra2 that's in my directory. And it'll tell me, oh, well, you're missing arguments. You need a configuration file, a points file, and a win file. So even though I've got a Python notebook, and maybe you're comfortable running the code in a Python notebook, you can also run it on the command line. And that's true for all of the codes, all of the numerical models that are implemented on Victor right now. I think all of them. So anyway, I'm going to go back to the notebook. Okay. So this is some stuff we need, right, to run this code. And you're probably familiar with some of it, like matplotlib or numpy, and other stuff looks a little bit shaky to you. Okay, so one thing I need to run the Tephra model is I need to know what the win field is, right? I have to know about VW and VY. No, sorry. WX and VY from my previous code, right? I have to know that. So Tephra2 asks you to provide a win file. And so if I click on this win file, I can see here's some win data. And that's the form of win data required to run Tephra2. And this corresponds to elevation above the surface of the win field. This corresponds to the velocity of the wind field. The second column is the velocity of the wind field in meters per second. This meters elevation. This is above the ground surface. This is velocity in meters per second. And this is the direction, the azimuth of the wind field. So Tephra2 is going to resolve this into the components, the velocity components of the wind field. It's asking us for input, the wind speed at a given elevation, and the velocity of the wind field, and the direction the wind is blowing toward. Okay, so often a meteorologist will say it's at least in the US, I'm not sure if this is true everywhere, but in the US they'll say it's a southerly wind. And that means if you face to the south, the wind is blowing in your face. So a particle is transported from the south to the north, right? So this is the azimuth the wind is blowing toward. Okay, so we get this this data file, this MyWind data file. That's one of the inputs we need. Tephra2 does a simplification. It assumes that the wind field does not vary laterally. It only varies vertically above the volcano. And so you don't see any X's and Y's in here. This is just the wind field as a function of height above the volcano. All right, so that's that. Now what we do here is in this notebook that Sam wrote, it goes out and it fetches wind data, right? It fetches the wind data from a repository of data. And this is the Copernicus, what is it called? Copernicus Climate Repository. And so what do you do here? So that's what these import commands are for, is to go out and get that data. And so you specify your coordinate location. Your latitude, longitude for your particular spot, where you want to get the wind field. You specify the month, the year and the day, and the hour of the that you want wind data for, right? And it goes out and finds. Go down here. It goes out, does some rounding and stuff like that to make sure everything is okay. But it goes out and finds the data, right? it hits this data, this site, and it finds that data. So what are the wind data? They're actually also a model. So reanalysis data put together by NOAA or this Copernicus data set, essentially what they do is hourly or 4 times a day, they will calculate the wind velocity as a function of height everywhere on Earth. And so it's a numerical model that's fit to observed wind data during that previous interval. So it's a forecast. And they go back and actually, they kind of hindcast. So they're a little bit behind, and they'll update the data, after they run the simulation for what it is now. So it's a little bit behind, but for our purposes, it's pretty cool because you can just go out and fetch the data. And then we put it into its velocity components. We translate the azimuth into the azimuth and the speed into those velocity components and so on that Tephra2 uses. And we create a wind file. So this file is generated not by you as a user, but by you specifying a time and a location, and Copernicus provides that data. You don't have to do it that way. You can just build wind data file by hand, or you can think about it probabilistically or something like that. But it's pretty. His demonstration of fetching that data is pretty good. Okay, then Tephra2 has a configuration file, and so these are parameters that are used in Tephra2 to simulate the amount of tephra that's going to accumulate on the ground during a volcanic eruption. So obviously some of these parameters are pretty simple to understand. You need a vent easting and northing, right? You need a vent elevation. You need a plume height. So that's how high the plume is going to go in the atmosphere. You need an eruption mass. There's a median grain size and a standard deviation of grain size. So we assume the grain size distribution is log normal. A couple of people have modified Tephra2 so that you don't have to make that assumption if you're interested in like a bimodal tephra distribution or something by grain size. Let's see. Well, a couple different people have done that kind of alteration to the code. This one just assumes the median grain size and standard deviation of grain size. And so you specify those. And this code, this script, then generates a log file, which essentially stores this information, and that's used as input for the Tephra2 code. So basically, when you enter values here, like the eruption mass is 1 times 10 to the 10th kilograms, the plume height is 1,200 meters, you're building this configuration file, right? So this is an example of a configuration file that will be built from that Jupyter notebook. Now, there's no reason you can't go in and build your own model, right? Build your configuration file directly. But the notebook is just designed to be a relatively simple way to do that, to provide you with that. And then there's some additional parameters, and we kind of break it out into these common parameters that are sort of associated with eruptions, and then additional parameters. Fall time threshold is a concept that Costanza Bonadonna came up with. And the idea is that diffusion actually changes as a function of the total particle fall time in the atmosphere. And so basically this comes out of meteorological studies where you can use Fickian diffusion or power law diffusion to describe how the particle's moving through space. And so for some eruptions, that fall time threshold is pretty important. If you look at the change in thickness of the deposit as a function of distance from the volcano, kind of decays exponentially. Well, some deposits have sort of a kink in that curve, and that's due to this change in the diffusion loss. There's a bunch of literature out there about that. There's different plume models. The particle steps is how we discretize the atmosphere and the particle size distribution. We have lithic densities and pumice density, eddy constant, some parameters that control the shape of the volcano column. So there's a lot there. You don't have to mess around with that too much. You can use default values or whatever. And so then you build, so that builds the configuration file, which I just showed you. And then you need one more file to actually run the code. Sorry, this gets long-winded, but it is. You need a grid file to run the code. And that's where you calculate, where you want to calculate the accumulation of tephra on the ground, say the mass loading, the kilograms per square meter, and the grain size distribution you expect to see on the ground. And so this creates that grid. So here I'm using a grid spacing of 1,000, a grid radius, that is how far away from the volcano you're going to do the calculation, and the elevation the tephra is falling to, the elevation above sea level the tephra is falling to. Okay, so this just builds that grid, and the grid file is pretty boring. Looks like that, right? So that's the UTM coordinates of the places where you're calculating the tephra fallout. Okay, and so then you run it, and when you run it, here we run it, and this does a couple cool things which you might have heard about from Sam before, but it might not have clicked for you. One thing it does is it goes and checks the current version of Tephra2 that's on GitHub. So you know, a lot of people store codes on GitHub. This will go pull the current version of Tephra2 off of GitHub. It'll compile it on Victor and it'll run the code. So that's pretty cool. So say Laura Connor or I or Costanza Bonadonna changes the code, and you want the most updated version. You don't want the version from 1999 or something like that. So so it'll go pull that process, and then this command actually runs Tephra2. You can see it passes it the config file that we built up there. It passes it the grid, which we built up there, and it passes it the wind file, which we built up there, and we pass it the output to this file Tephra2 CSV. So it'll tell you it's running, blah blah, and this part's not really well developed right now, but we're just plotting simple isomass maps to give you an idea of what the output's going to look like from the code. The main thing you probably want is this file, which is a CSV file that stores the output from Tephra2. This one has a lot of data points in it, so whoops, oh, because I didn't run it. Oh no, I did run it. Okay, so here's the location of the point, the elevation of the point, the total mass accumulated there, sort of obviously in a very thin part of the deposit, and then the mass by grain size. So you can look at the grain size distribution at a specific point. I'm going to try to find, oh, here's a little more tephra accumulated at this point, and you can see the grain sizes for that variation. So that's running the Tephra2 model. I just point out this is a pretty cool code, but it's really meant to be a sort of a demonstration of a workflow, right? So let's say you wanted to do something different with Tephra2 than simply make an isomass map. Maybe you're interested in changing the configuration file within a range of parameters and plotting out the range of mass loading that's going to occur at one point, for example. That would be more of a probabilistic tephra fallout hazard assessment. Well, you would just rewrite this workflow, right? That's the idea behind this, is when we give you a workflow, we can talk about how you might change the workflow to fit the problem that you have in particular. So, or maybe you're interested in matching the tephra thicknesses that you see, that you actually measure in the field, that you know erupted from some volcano, and you want to know the eruption source parameters that produce that. You can do that too by coupling Tephra2 to an inversion problem, you know, and I showed you a couple of simple inversion methods a while back, a few weeks ago. So there's a lot of options here. There's a lot of power here for running these kinds of codes. So this is not meant to be, you know, oh, I'm just going to run this and see what happens. The idea is to try to work on modifying these scripts to suit your needs. So if anybody's particularly interested in Tephra and wants to build a script that does something specifically, you know, write about it in Slack, and we'll, you know, talk about how to modify Sam's script here to fit the, you know, fit the approach that you want. Can be pretty useful. Laura, Connor, and I are working on a project right now where we're looking at tephra dispersion from in a distributed volcanic field, and we ran 30 million simulations. So that's the nice thing about being able to use a tool like AWS or you know, this kind of Victor resource to actually do that kind of modeling. All right. Well, I'm tired of talking. You're probably tired of listening. So I'm going to stop there, and I'm going to save the recording. I'm going to turn off the recording, and you guys